Okay, so let's continue our discussion of equilibrium. So we said that if you have a reaction, how far will it go? It will go to the extent where the reaction quotient becomes equal to a constant at a given temperature for that reaction. Okay, so Q, we say the reaction quotient approaches a constant value, which we call your equilibrium constant at a given temperature. Okay, so now we're going to talk about what happens if your reaction is already at equilibrium. How can we make it, how can we disturb it? How can we, what happens if we try to disturb it? Okay, so the key principle we need to know to understand what will happen and to predict what will happen is known as Le Chatelier's principle, which says that if a stress is applied to a system that's already in equilibrium, okay, it will shift or it will react in a manner that tends to counteract the stress. So examples of stresses that you can apply to a system at equilibrium, let's say you've got something that's already at equilibrium, you can add more products or reactants. Okay, so let's say you have a reaction between, let's say, HX gives you H plus X minus, for example. Okay, it's just a generic reaction. You can add more H plus from some other source like HCl. Okay, that's adding more products. Okay, or you can remove, or you can add more reactants. Okay, or you can remove products or reactants. You can change temperature. Okay. One way you might be able to remove a product, for example, is if you add something that might react with X minus. For example, let's say you add a source of silver ions that might react with your anion to give you a precipitate of AgX. Okay, so that would be a way of shifting the equilibrium. Okay, so you can change your temperature, or you can change the total volume. Okay. Especially if you're dealing with a gas, that can make a big difference. So why is the equilibrium disturbed? Essentially, what happens here is, okay, we're going to classify our stresses into two kinds: stresses that are applied under constant temperature. Any stress that causes Q to change will affect your equilibrium, right? Because if Q has changed, if you did something to change Q, then it's no longer equal to KQ. So it will shift in a manner that will restore the value of Q to what KQ is, right? Or you can change the temperature. That will also lead to a stress, because if you change the temperature, then that means you've changed the KQ. So whatever Q you have there is no longer equal to KQ. So the net effect of a stress then on a system that's already at equilibrium is, by applying a stress, you're making Q not equal to KQ. Either you're changing the Q while maintaining KQ, or you're changing the KQ if you're changing the temperature. So let's illustrate that. Let's look at this reaction right here. HSO4 minus bisulfate ion plus water gives you sulfate plus H3O plus. Assuming constant temperature, what would happen if I add potassium sulfate? What do we know about potassium sulfate in water? It gives you potassium ions and sulfate ions. So if I have more sulfate ions, look at my Q right here. Sulfate times hydronium over HSO4 minus, and that's just water. That's activities 1, right? So what would happen if I have more of this? Q gets bigger. So temporarily, as a result of the stress, we say, or momentarily as a result of the stress, Q has gotten bigger than KQ. So which way will the equilibrium shift? Which direction will the reaction take in order to counteract that effect? Okay, it shifts to the left, right? Because here's a simple way of thinking about it. If you're putting more sulfate in, the system will try to counteract what you did. If you put more sulfate in, it will try to get rid of some of it, so it will shift to the left. Okay, add more products, shift to the left. Now, why did I specifically mention solid here? The reason is that if you add, let's say, potassium sulfate that's already in solution, then if you're adding more sulfate, you might be adding more sulfate, but you'll also be changing the volume. So that can be complicated here because you're changing all the concentrations when you change the total volume. Okay, so you have to be careful when you do this thing. So, like if I said just add a very dilute solution of potassium sulfate, then it's not going to be, uh, the impact's not going to be as much as if you did solid potassium sulfate. In fact, it could be the other way because if you add more water, what happens? Okay, if this concentration drops, if that concentration drops, that concentration drops, the total Q could actually drop. Okay, like if you double all the volumes, this will be cut in half, that will be cut in half, and that will be cut in half. The whole Q would become half of what it was, so it will actually shift to the right. Okay, so the net stress that you've done is adding water if you're adding a dilute solution of potassium sulfate. Let's look at this same equilibrium reaction. What if you add sodium bisulfate solid? This is going to be a source of what? What does this do in water? It dissociates and gives you sodium ions and bisulfate ions. So will the reaction shift to the left or to the right? If you add more reactants, you're making Q smaller. If Q is smaller, which direction will it take? It goes to the right to make it big again, okay? So correct answer is shifts to the right. What happens if I add barium chloride solid? What does barium chloride do in water? Gives you barium ions and chloride ions. Oops. Okay. Are we adding any reactant, removing any reactant? Okay, this is where your earlier class is going to haunt you because now you have to remember your solubility rules. Barium and sulfate will precipitate. So what does barium do? It actually removes sulfate ions. It forms barium sulfate solid. So which way will the reaction shift? To the left or to the right? So it will shift to the right. You're removing sulfate, so what happens to this number right here? This drops, right? So Q drops. If Q drops, then the reaction shifts to the right. Okay? Let's look at this. What happens if you add more water? Actually, I covered this earlier. So let's say you add water. Let's imagine you add enough water so you double the volume. Okay? Will it shift to the left or to the right? Okay. Let's just imagine a situation where you add so much water, so you double it. So this is now half of what it was. This is now half of what it was, momentarily anyway. And this is now half of what it was. What happens to Q now? It's going to be half of what it was, right? Because times this 1/2 and that 1/2 will cancel out. You have an extra 1/2 factor in the numerator. So now system will now respond by trying to increase Q, so the reaction shifts to the right. Okay. Here's a way of looking at it in terms of the system counteracting what you're trying to do. What is it you're trying to do when you add more water? You're just making the solution more dilute, right? More water makes the solution more dilute. So what the system tries to do is to counteract that, is to make more solutes. So here you have 1 mole of solute on the left being replaced by 2 moles of solute. So that's the opposite effect. So the effect of the immediate effect of putting more water is to lower the concentration of everything, right? So the counteracting effect, according to Le Chatelier's principle, would be to produce more solid particles, and it shifts to the direction of having more solid particles. Okay, here, a closed bottle of a carbonated drink. Okay, so if here's your soda, let's make this Coca-Cola. So what's the shape of a Coke bottle? Like that. All right. They don't come in those bottles anymore, huh? All right. So the 4 atmospheres of CO2 here, CO2 gas, and you've got CO2 in your soda. What happens if the bottle is open? Here's the equilibrium. It's the equilibrium between CO2 in the gas phase and CO2 in the aqueous solution. And then you open it up. What happens when you open it up? Equilibrium shifts to the left or to the right? Or does it have no effect? When you're opening it, what are you doing? What's the pressure outside the bottle? How much CO2 is in the air around you? You have 1 atmosphere of air around you, but how much of that is CO2? Very low, right? It's about 20% oxygen, almost 80% nitrogen. You have trace amounts, strictly speaking, you have very, very small amount of CO2 in the air. So you lower the amount of CO2 in the air that's above, in the gas that's above your soda, your liquid. So what happens? If you lower the pressure, what will it try to do? You lower the amount of CO2 in the gas, what will your system try to do? What's the opposite of removing CO2 gas? So the net effect of opening the bottle is to remove CO2 gas. So which way will the reaction shift? Shifts to the left, right? You're removing CO2 gas, so you shift to the left. And what's the physical manifestation of that shift to the left? CO2 from the liquid is going to bubble out of your soda. Okay, so that's what happens. Okay, now we've talked about this earlier. Okay, basically what we said was that the solubility of a gas in a liquid is directly proportional to its partial pressure in the gas that's in equilibrium with that liquid. That was Henry's law. Okay, so the concentration of A, if A is a gas, okay, concentration of A in the liquid that's dissolved in a liquid is directly proportional to the partial pressure of that in the gas, and that ratio of those two is what we call the Henry's law constant. So you can see this ratio, concentration of A in the liquid over partial pressure in the gas, that's really the equilibrium constant for this. Okay, so Henry's law constant is really nothing more than just another equilibrium constant. Okay. Here's another example. You have a closed container. Liquid water is in equilibrium with water vapor. So I've got liquid water here, and I have water vapor gas there. So you got equilibrium. What happens if I add sodium chloride to my water? Vapor pressure is, remember your colligative properties? What's the answer to this one? You add a non-volatile solute to a liquid, what happens to the vapor pressure of the liquid? It's lowered, right? Raoult's law. P of water is going to be P star water times the mole fraction of water, right? So it's lowered. The vapor pressure is lowered. Okay. How is that illustrating Le Chatelier's principle? By putting sodium chloride in your water, what are you doing to the concentration of water, to the activity of the water? Okay. Your reaction quotient is partial pressure of the water vapor, okay, this is gas, over the mole fraction of water. So if you're contaminating your liquid, you're lowering the mole fraction of your water in the liquid, what happens to Q? It goes up. And so if Q goes up, which way will the reaction shift? If Q increases, right, mole fraction of water goes down, Q increases, which way will the reaction shift? Momentarily now you've made Q bigger than KEQ, so the reaction shifts to the left to make Q smaller again. So shifts from gas to liquid. That's why your vapor pressure of water is lowered. So that's one way of looking at Raoult's law. Okay? So in fact, if you look at right here, here's Raoult's law, right? P sub A is P sub A star times mole fraction of A. If you divide both sides by XA, you can see that P sub A star is really nothing more than just another equilibrium constant. Okay? So you can think of Raoult's law in terms of a reaction where you think of it as like a reaction, as if it's a reaction where you have liquid water as your reactant and gaseous water as your product. You can treat it that way. Here's another example. Let's say you have an equilibrium mixture of NO2 and N2O4. What happens if the mixture is compressed? Equilibrium shifts to the left, or equilibrium shifts to the right. Ready? We're going to assume it's constant temperature. Unless otherwise specified, we're going to assume all of these stresses involve constant temperature, okay? Will it shift to the left or it shift to the right? Let's see. I'm guessing 50-50. Let's see. Yep. Okay. All right. What happens to your pressure if you compress? Pressure is equal to nRT over V, right? So what happens is the volume gets smaller. Smaller volume, smaller denominator, pressure increases, right? So let's say this is doubled and this is doubled, just for illustration purposes. So what happens to Q? Let's say this was 0.1 and that was 0.1, just for illustration. Let's say this is 0.5 for illustration purposes. So now, okay, remember this is raised to the power 1 and this is raised to the power 2, right? So now I multiply this by 2 and I multiply that by 2. What happens to my Q? It's the square is in the denominator. So it's cut in half, right? So my Q becomes smaller, right? And so if Q becomes smaller, what happens? Where will it shift? Shift to the right. Okay? So what's the net effect here? Let's take a look at it qualitatively, okay? So you can predict it without going through this expression for Q. Qualitatively, you look at it this way. When you're compressing it, you're raising the pressure, right? Pressure is directly proportional to number of moles. More moles of gas, the higher the pressure. So if you're compressing it, but that leads to a momentary increase in the pressure, okay? What will the system try to do? What's the opposite of increasing the pressure? Decreasing the pressure. So how will the system try to decrease the pressure? It will shift to the direction with fewer moles of gas. Okay? So here's what you do. Increasing the overall pressure causes the system, in response to that, okay, you expect the shift to the side with fewer moles of gas. And which side has fewer moles of gas? The right side. If you shift to the right, you're replacing 2 moles of gas by 1 mole of gas. And that's why our prediction is for it to shift to the right. So the correct answer in this case is shifts to the right. All right. What about a change in temperature? Well, a change in temperature affects KEQ because KEQ is only a constant at a given temperature. Now, the Van Hoff equation, okay, from chemical thermodynamics, you can show that the dependence of the equilibrium constant on temperature is given by what's called the Van Hoff equation. It says natural log of KEQ would be negative delta H over R times 1 over T plus C. So this is one of the connections between heat measurements and equilibrium. The equilibrium constant actually depends on the delta H. Okay? So you've seen a similar equation to this earlier when we talked about the Clausius-Clapeyron equation, right, and the Arrhenius equation. Basically, what does this thing say? If I were to plot this on my y-axis, and I were to plot 1 over t on my x-axis, what would be my slope? This right here, negative delta H over R, is going to be my slope, right? And C is going to be my y-intercept. Y equals mx plus b, right? So if I were to plot that, what would I get? Well, 2 possibilities. Natural log of KEQ versus 1 over t. It's either I get a graph that looks like this, okay, or I get a graph ln KEQ versus 1 over t that looks like this. This is a positive slope and a negative slope. Ah, I got it wrong. So I gotta switch. This is a negative slope and this is a positive slope, right? And what's the slope equal to? It's negative of delta H over R. Okay? So, all right, you remember which side of my x-axis is low temperature and which side is high? If temperature is high, what's my value of 1 over t? Smaller. So high temperature is on this side, right? And low temperature is on this side. Okay? And so high temperature over here, low temperature on this other side. Let's take a look at this case where you have a negative slope. So you say slope is equal to negative delta H over R. So what's our delta H then? Delta H is equal to R, negative R times the slope. So what's negative R times a negative number? You have a negative times a negative slope. Negative R times a negative slope will give you a positive delta H. So we say that if the graph looks like this, our reaction is endothermic. Similarly, if a graph looks like this, our reaction is exothermic. Delta H here will be negative. Okay? So, is that consistent with Le Chatelier's principle? Well, let's see. Endothermic means it's favored at high temp or low temp. KEQ is larger at high temp, right? So this one right here, we say, for this case, KEQ is larger at higher temperature. In other words, the products are favored at high temperature. Why is products favored at high temperature for an endothermic reaction? What does an endothermic reaction mean? If you have reactants going to product, endothermic means what? Heat is absorbed or released? Okay, so heat, you can think of heat as a reactant in an endothermic reaction. Okay? So, what if I were to raise the temperature of my reaction mixture? What am I essentially doing? I'm putting in more heat, right? So which way will the reaction try to do? Which way will the reaction try to shift? The opposite of adding heat is removing heat, so the reaction shifts to the right. So that favors the endothermic reaction. Okay? So similarly, if you have an exothermic reaction, what would you have? Reactant gives you products plus heat, right? If I were to increase the temperature, what will happen? It will favor the reverse reaction. Okay? So think of it this way. Endothermic reactions are really the way you write it. You classify it as endothermic or exothermic depending on how you write it. You're actually, when you say it's endothermic, you're actually referring to the forward reaction, because since the reaction is reversible, if it absorbs heat one way, if it goes the opposite way, it must release heat, right? So we say an endothermic reaction is one where the forward reaction is endothermic. So forward is endothermic. The reverse, in fact, is exothermic. That's another way of looking at it. So if you have an endothermic reaction, the forward reaction is endothermic. That's favored by high temperature. Whereas if you have an exothermic reaction, okay, reactant gives you products plus heat, okay, then the reverse reaction is endothermic. So we say the forward is exothermic, then the reverse is endothermic. Okay? So heating favors the endothermic direction. So let's look at these questions then. If you have this reaction, fictitious reaction, is this exothermic or endothermic? Heat's on the reactant side. So that means it's endothermic, right? It's endothermic going forward. It's exothermic going in reverse. Okay? So if a mixture of A and B is at equilibrium, what would happen if the temperature is raised? Well, when the equilibrium is reestablished, A would be what? Which way will it shift? Shift to the right. So A would be lower or higher? If it shifts to the right, lower, and B would be higher, and the new KEQ will be higher. Okay? Let's look at this one. Is this exothermic or endothermic? Delta H is negative. This is exothermic, right? So you have heat on the product side. Suppose A is yellow and B is blue, and a mixture of A and B is green. What happens if you increase the temperature? Which way will it shift? It will shift to the left, okay? So what happens? So the color of the solution will be what? More yellowish or more bluish? A is yellow, so it's going to be more yellowish, right? And the KEQ will be higher or lower? More reactants. What happens to KEQ? Lower. Okay, let's take a look at one last question. Consider the vaporization of water. And let's imagine you have a sample of water in an enclosed container at equilibrium. Okay? What would happen if the temperature is raised? So you've got liquid water and gaseous water. The vapor pressure of water will blank, and the new KEQ will be blank. What's the correct answer here? Well, let's see. Liquid to gas, that's an endothermic process, right? So that is favored at high temperature, according to the Chatelier's principle. So you would expect that water vapor, the gaseous side, product side in this balance equation, will be favored at higher temperature. So the vapor pressure of water will be higher. It will increase. Okay, so it's not this. There will be a net shift in the forward direction, and the new KEQ is going to be, well, what's our KEQ here? You can think of it as partial pressure of water in the numerator and mole fraction of liquid water in the denominator. And or you can say this is essentially equal to 1. Okay. Well, it is 1 since you're dealing with pure water. And so your vapor pressure is going to increase. So the equilibrium constant is really nothing more than the vapor pressure of water is really nothing more than an equilibrium constant for this reaction. That is why the Van Hoff equation for this, okay, ln KEQ is equal to minus delta H over R, 1 over T plus a constant. It's essentially the same as the Clausius-Clapeyron equation, which is ln of P, the vapor pressure, is equal to minus delta H vaporization over R times 1 over T. Let's see. And delta H vaporization is a delta H for this so-called reaction. Okay, if you can think of this as a reaction, okay, then the delta H for this reaction, in quotes, it would be the delta H for the vaporization of water. All right, one final comment about a catalyst. This one's about a catalyst. What would be the effect of a catalyst on equilibrium? Well, a catalyst speeds up a reaction without being consumed, and the way it does this is by providing an alternative path that has a lower energy of activation. So what a catalyst does, it simply speeds up the establishment of equilibrium. It speeds up the approach of your reaction mixture towards equilibrium. But it's not going to affect the position of equilibrium. Position of equilibrium, your equilibrium constant depends only on temperature and what the overall reaction is. Okay, so effect of a catalyst would be faster approach to equilibrium, but no effect on the position of equilibrium.